Hey guys, this is for your 10.4 homework assignment. I just wanted to do some problems with you to kind of help you think through some of these. I'm going to do some of the odds because the answers to the odds are already at the back of the book, and then save the evens for you guys because those are typically the ones that I grade to see if you got the right idea or not. So before we get started here, the top bullet points here are going to be really important for most of the assignment. The idea here is that we have two events happening, or we have two events that we're looking for potentially, and we call them A or B. They don't have to be A or B. I think later in the book you'll see an event called E. It doesn't really matter, but they just represent two different events. So if you want to find the probability of two events happening with one trial or something like that, there's two different formulas that you need to use, and it depends on whether the events are mutually exclusive, meaning they can't possibly happen at the same time, or whether they're inclusive, which means they could potentially happen at the same time. So here's some Venn diagrams that kind of represent that, and there's like a good diagram of this in your book on page 653. That kind of shows you, but the idea is we represent outcomes in the sample space with like Venn diagrams. So this is like the outcomes for event A could never overlap with the outcomes for event B. There's no way for them to happen at the same time. That's what we call mutually exclusive. This one is for inclusive, where you could potentially have event A and B happen at the same time, and you represent that with the A and B overlapping, and that little overlap is where A and B, the events are happening at the same time. So let's take a look at some examples, but we need to keep these in mind that there's two different scenarios that we have here. Let's start with number 9. Okay, and number 9, we're talking about rolling a die, or they say a number cube, which we're assuming is a 6-sided number cube with numbers 1 through 6. So we're going to roll, and we want to find the probability of each event, and 9 is even or 3. Okay, so the first thing I would do is determine if these are mutually exclusive or not. Okay, or can they happen at the same time? Can you roll an even and a 3 on one roll? The answer is no, because 3 is odd. So what you do is the probability of even or 3, since they're mutually exclusive, is just the probability of even plus the probability of 3. Okay, so the probability of even, we know that there's 3 even numbers in the sample space. The sample space, just so we're clear, is 1, 2, 3, 4, 5, and 6. Okay, so there's 6 things in the sample space. So the probability of even, there's 3 even numbers over the number of outcomes in the sample space. Okay. Then how many ways are there to get a 3? Well, there's only one way to get a 3 from the sample space, right? So you add those together and you get 4 out of 6, which reduces to 2 over 3. Okay, so in that situation, they're mutually exclusive, they don't overlap. You can just add the two probabilities together. You can also just think of this conceptually without breaking it down, and just think, okay, well, how many ways are there to get an even or a 3 without counting the same thing twice? How many unique ways are there of getting an even or a 3? Well, I can get a 2, because that's even, a 3, because it's a 3, a 4, because that's even, or a 6. So you could just say, well, there's 4 ways to get what I want out of 6 things in the sample space. So you can kind of think of it, formula-wise or conceptually, and either way will get you to that 2 over 3, excuse me. All right, let's look at one that is inclusive. So this is number 11, and we want the probability of less than 4 or just the number 1. So we want the probability, let's see, I'm going to use a symbol here so it's a little bit quicker, of getting less than 4 or a 1. Okay? Well, these are actually inclusive. They overlap because 1 is less than 4, so it falls into both categories. The things that are less than 4 are 1, 2, 3, and the things that are 1 they're just one of them. Okay, so they overlap. So this would be the probability of less than 4 plus the probability of 1, but then we have to subtract out the probability that they both happen at the same time. So how do you get less than 4 and 1 at the same time? That would just be getting the 1 again, basically. Okay, so this is a less than 4. Okay, so probability less than 4. Let's look at our sample space. It's the same as up here, 1, 2, 3, 4, 5, or 6. Less than 4, there's a 3, a 2, or a 1. Those are all less than 4. So that's 3 out of 6. There's 3 out of 6 ways for that to happen. Okay, probability of 1, there's only 1, 1. So that's 1 out of 6. Okay, but notice, if I use this 3 over 6, that includes the 1, the 2, and the 3. But over here, that includes the 1. So I just double counted that 1. I counted that as 2 separate outcomes, and 1 is only 1 outcome. So what I have to do is I have to subtract out the ways for the overlap to happen, right? 1 is in both sets. Getting a 1 would be being less than 4 and 1 at the same time. So I don't want to double count that. All right, so it's 3 over 6 plus 1 over 6 minus 1 over 6, which ends up being just 3 over 6 or 1/2. Okay, so that's how you do it, kind of using the formula. It's the probability of the first outcome, the first event, plus the probability of the second event, and then subtract any ways, however many ways there are for them to happen at the same time. Now in this case, these guys are exactly the same probability. That is not always the case. A lot of times this is less than this one. So if you're thinking, oh, I'll just cancel those out every single time, they don't always cancel out. They just happen to in this specific example. You can also just think of this kind of conceptually, like we did up here, where you're thinking, okay, well, how many ways are there to get this one of these things to happen without double counting? So let's look at our sample space really quick. Right? We already know that there are 6 things in this sample space. So we're thinking about how many ways are there for for less than 4 or 1 to happen, but without counting the same thing. So this is less than 4, and this is less than 4, and this is less than 4. And then this is 1, but I don't want to double count that, so I just have 3. There's 3 options for me to get less than 4 or 1, because I don't want to count the same thing twice. Either way, you're going to get 1/2. Okay, whether you want to kind of write it out using the formula. This is just kind of a conceptual idea, though. You can use it as a formula, but it's also saying, look, if you have the same thing in happening at the same time, you got to subtract that out. Okay, or basically what this piece means is don't double count that 1. Don't count it twice. That's only 1 outcome, even though it works for less than 4 and for 1. Okay, number 13 is kind of going to be more of a complement idea. So the complement of an event is all the outcomes in the sample space where that event doesn't occur. Okay, so 13, we want the probability of not 1. Okay, well again, there's multiple ways to look at this. You could say, well, how many ways are there to get not 1 if you're rolling from a die? So sample space, again, is going to be 1, 2, 3, 4, 5, 6. So this is a sample space. There's 6 different possibilities there. How many ways are there to get not 1? 1, 2, 3, 4, or 5. There's 5 different ways for that to happen. So there you go. There's your answer. Notice, though, that not 1, the probability of not 1, is the complement of the probability of getting a 1, right? It's the opposite. So what you could do this. The probability of not 1 is equal to 1, 100%, minus the probability of getting a 1. Because this is basically the complement of this. Getting a 1 and not getting a 1 are complements of each other. So I could say, okay, well, the probability of not getting a 1 is 1 minus the probability of getting that 1, which would be 1 over 6. So 1 minus 1 over 6 is the same thing as 6 over 6 minus 1 over 6, which is 5 over 6. So you can say there's one way to get a 1, which means the other 5 options are not 1. And that's kind of how complements, that's kind of how they work. Okay, so that should help you get started on those. There's only, I think I gave you 7 problems from there, and I just did 3 of them for you, so hopefully you can get the other ones there. Okay, let's look at the next problem set. Now, in your book, they have a chart that they gave you, which is cool, and it's nice that they gave that to you, but I'm going to make a new chart that I think is a little bit more helpful. instead of writing so what they did in the book is they said, okay, the first roll is a 1. This represents your first roll, and this represents your second roll. The first roll you got a 1, and the second roll you got a 1. Right? And the first roll you got a 1, the second roll you got a 2. So what we're doing is we're taking like 2 dice and we're rolling them like you would do in like Monopoly or whatever, or craps if you're, gambler, which probably none of you are yet, I hope. But anyway, you got 2 dice and you're going to roll them both. Well, how many different options are there? How many different things are there in the sample space? Well, there's 6 options for this one and 6 options for this one. So if you multiply that, you get 36 different outcomes that you can get from rolling the dice. So check it out. This is a 6 by 6 grid, which means there's going to be 36 outcomes in here. And this is how they list them in your book. Okay, so the first dice is a 1, the second dice rolls a 1. And you're not really doing them one at a time, you're rolling them together, but you just, you have like die 1 and die 2. Okay, something like that. And you roll the first one, or roll 1 is like what you roll on the first die, and this is the second die. So you roll these 2 dice, and there's all these different options. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Or you get a 2 on the first one, and a 1 on the second one. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on all the way up until 6, 6. But instead of listing the different die, I'm going to list the sums, because a lot of the questions that you're going to do are you're going to list the sum. So what are all the different sums if you roll 2 dice? All the different outcomes for Monopoly or craps or whatever. So 1 plus 1 is a snake eyes right here. This would be 2. And let's do the other side, 6 and 6, because you're going to see some patterns. 6 and 6 is 12, so you can roll a 12. So double 1s or double 6s. Okay, now I could roll a 2 and a 1, which would be a 3 total, or I could roll a 1 and a 2, which would be a 3. Okay, check this out. If I roll a 3 and a 1, that's a 4. I could roll a 2, 2, which is a 4, or I could roll a 1, 3, which is a 4. Are you starting to see the pattern here? Okay, what if I rolled a 4 and a 1? That would be a 5. But a 3 and a 2 is also a 5. But a 2 and a 3 is also a 5. But a 1 and a 4 is also a 5. So you can see how, like, up across the diagonals, the numbers are kind of the same, and they're all going up. So we're going to get 6, 6, 6, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 8, 8, 9, 9, 9, 9, 10, 10, 10, 11, 11, and 12. So if you've heard like lucky number 7s or whatever, lucky 7, 7 is the most likely roll. Because there's 1, 2, 3, 4, 5, 6 ways to get a 7. It's the most likely that you're going to get a 7. These are just so these are all the outcomes are in the dark box. These are just labels on the other side. They're not sums. They're just labels for the first and second rolls. So inside that dark box are all the outcomes. And the most common option is a 7. So in craps, it's good to roll a 7 in certain scenarios. Okay, so there's all your 36 outcomes of sums that you could get. Okay, all right, let's look at some problems here and actually kind of put these together. So number 17 says roll a sum of 8 or a sum of 12. So there's 2 events here that we're looking for. So we want to find the probability of a sum of 8 or a sum of 12. Okay, the first thing we have to ask ourselves, or what we should ask ourselves, is this disjoint, or excuse me, if it's mutually exclusive, that's another way to say it. Mutually exclusive and disjoint mean the same thing. It means non-overlapping. So are these events mutually exclusive, or are they inclusive? Right? Can I roll a sum of 8 and a sum of 12 at the same time? No, there's no way to do that, right? You can roll, there's a lot of different ways to roll an 8, and there's one way to roll a 12, but you can't do that, at the same time. You can't roll 2 dice that sum to an 8 and sum to a 12. So let's take a look at how many different options are there. Now, remember, in this sample space, there's 36 total boxes, right? It's a 6 by 6 grid, so 6 times 6 is 36. There's 36 total options. How many ways can I roll an 8? Well, there's 1, 2, 3, 4, 5 different ways for that to happen. Okay, how many ways are there for me to roll a 12? there's 1 out of 36 ways for me to happen. So we're going to add those. There's no overlap in between these. These are mutually exclusive or disjoint, and so we don't have to worry about subtracting the overlap because there is no overlap, and we just get 6 out of 36, which we can reduce to 1 over 6. Okay, so we basically use this formula right here for the mutually exclusive. Just add the two different probabilities if they are mutually exclusive, which they are in this case. We're going to see some cases where they're not, like number 19. Okay, so number 19, we want a sum of less than 7, or, this one maybe is disjoint as well, or mutually exclusive. The next one I think is. A sum of less than 7 or greater than 8. So probability sum, let's abbreviate a little bit. Sum of less than 7 or sum greater than 8. Okay. Okay, do those overlap? Is there anything that can be less than 7 and greater than 8 at the same time? Well, it doesn't really make sense, right? You can't be lower than a number 7 and then bigger than 8 at the same time. So these are also mutually exclusive or disjoint. So what we need is just these separate probabilities. We need the probability that the sum is less than 7, and we're going to add that to the probability that the sum is greater than 8. So let's look at all the ways we can get an outcome where the sum is less than 7. So let's start with 6, because that's less than 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there's 15 outcomes where we're getting a less than 7. Okay, so that's that probability. We're going to add to that the probability of getting a sum that's greater than 8. So that would be all the 9s, 1, 2, 3, 4, plus the 10s, 5, 6, 7, the 11s, 8, 9, and then 12 would be 10. So there's 10 ways for that to happen. Okay. And there's no overlap, so we don't have to worry about that. But we add these together, we get 25 over 36, which is not going to reduce. So this should be our answer. Now, just to double check, let's find the complement to see if we're right. So how many ways can we get not this happening? So how many ways are there to get a 7 and an 8? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I add 11 to 25, I get 36 because they're complements of each other. So the probability of less than 7 or greater than 8, the complement of that is getting a 7 or an 8, which is 11 over 36, and that works out good. So that's kind of a check. Okay, 21, a sum of less than 3 or a sum of less than 10. Probability, sum of less than 3 or sum of less than 10. Okay, so we're going to definitely have some overlap here because these things can happen at the same time. So we want the probability that the sum is less than 3 plus the probability the sum is less than 10, and we're going to subtract the probability that the sum is less than 10 and less than 3. Let's go less than 3 and less than 10. Now, if you think about it, like anything less than 3 is also less than 10. So it actually turns out that this and this are the same thing. So those are going to cancel. We basically just want anything less than 10 is going to work for this. So we're going to look at it a couple different ways just to make sure that we understand what's going on here. So how many ways can we get less than a 3? Well, there's one way to do that out of 36. How many ways are there for us to get less than 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. There's 30 ways to do that. But guess what just happened? I just counted this twice. It was like, how many things are less than 3? Oh, sorry, less than 3. Yeah, how many sums are less than 3? 1. How many sums are less than 10? There's 30. But this is both less than 3 and less than 10. And so I counted it twice, which means I need to subtract the ways there are for it to be less than 3 and less than 10 at the same time, which is that 1 out of 36. Okay, So this is going to end up being 30 out of 36, which simplifies to 5 over 6. Okay, now another way to think of this is just to kind of, think logically instead of using the formula, and just think, well, how many unique ways are there for one of these things to happen? In other words, like don't double count. So if you're like, okay, this is one outcome that works because this is less than 3. Okay, now I want to find all the outcomes that are less than 10, but I don't want to double count this already. So I counted this 1, that's 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Right? I didn't count this twice this time. I just wanted all the unique possibilities. And since I already counted that when I was looking for stuff that was less than 3, I'm not going to recount it when I look for stuff that's less than 10. Either way, you're going to get 30 out of 36, which gives you 5/6. So the formulas can be helpful. You can write them out exactly like they are, and you can follow that template. But the formula is also just kind of a way of reasoning of, looking and say, hey, look, if you got stuff that overlaps, you have to subtract the ways that both of those events can happen at the same time. Otherwise, you're going to count the events here and here, double count them, and then you're going to have too many things. So that's kind of the key there. All right, last problem set here we're going to take a look at, and this is finding complements. So in your book on the top of page 655, there is 3 different kind of formulas that look kind of like this. There's 3 different versions of this statement. The main idea that we talked about, we'll write all 3 here, is the probability of some event A plus the probability of its complement is always going to be equal to 1. These things are going to be mutually exclusive. They can't happen at the same time. So it's like the probability of rolling an even and the probability of not rolling an even. Well, if you put those 2 probabilities together, that's all the outcomes there are. You can't roll, you either roll an even or odd. So you add those together, you're going to get 100%. We can rearrange this equation in a couple different ways. We can say, okay, look, if you want to find the probability of a complement of something happening, it's just 1 minus the probability of the event. And there's the one other way to write this is if you want the probability of an event, you can say that that's 1 minus the probability of its complement happening. Okay? So in 31, they're giving you the probability of some event happening and asking you to find the probability of its complement. So we're going to do, so 31 they say probability of some event E. Now they call it E instead of A. It doesn't matter. It's like a variable. Is 4 out of 11. So they're saying the probability of this event is 4 out of 11. Well, the complement of this event has to add, the probability of the complement of the event has to add with this to give you 100%. So if I want to find the probability of E complement, I have to take 100% and I have to subtract the probability of the event happening. So this would be 11 over 11 minus 4 over 11, which is 7 over 11. So if they give you the probability of an event, you've got to find basically the opposite of it, I guess, or, well, it's the complement, but you got to find the number that when you add it to this, you get 1. Or you got to find the 7 other options. This is 4 outcomes out of 11 total in the sample space. Well, what are the other 7 options? Those are going to be in the complement. Okay, we did examples of this with dice and stuff like that. So let's just look at that really quick just to explain this one more time. Let's say this is your sample space, right? We're rolling a die. Oh, let's put a 4 in there. This is your sample space, right? And you want to find the probability of getting, the probability of 1 is 1 out of 6. What's the probability of the complement, which would be not rolling a 1? It's the other 5 options, right? Here's the probability of rolling a 1. Here's the probability of not rolling a 1. It's the other 5 options. So that's what's happening here. There's 11 things in your sample space, 11 events in your sample space. 4 of them are what happens when E, or 4 of those outcomes, E is true. So that means there's 7 other outcomes that aren't accounted for. There's 7 other outcomes where E doesn't happen. That's the complement. Okay, so that should be pretty easy. All you pretty much have to do is take the number that they give you, subtract it from 1, and you're good to go. That's pretty much it. But conceptually, that hopefully will help. Anyway, that should help you get started with your homework, or that's, not quite half of it, but it's a big chunk of it. So I hope that helps, and as usual, if you have questions, let me know. You can email me or leave a comment on your homework, and good luck.